The next thing we're going to consider is command query separation. Now this is a term also coined by Bertrand Meyer, who coined design by contract, and it's not an accident. These two approaches go very well together. So the very simple idea here is that when you're writing methods of your classes, we should completely separate commands, which might change the state of an object, from queries which return a value. In other words, any operation should either be a command or a query, but no operation should ever both change an object state and return a value. Okay? Now, the advantage of this is that then things which are queries can, because they're guaranteed not to change an object state, it doesn't matter how many times you run them. And that means that they can be freely used in contracts. You don't have to worry about, running the operation, in other words, checking the contract, actually changing a thing. In UML, there's a standard property which can be applied to an operation, query, and that indicates that they guarantee not to change anything, and it's having that property which makes it legal to use an operation in a constraint. So this fits with that. A thing to notice is that the value here comes from the fact that queries do not change an object state. Okay? It doesn't really matter whether a command does or does not return a value. On the other hand, following this separation strictly so that commands never return values is easy to do, but as we'll see, it has a disadvantage as well. So you might want to follow the modified version of a command query separation, in which you just say there are some queries which do not return, there are some queries which do not change an object state. Okay, so in order to talk about that, we first need to talk about the law of Demeter. And this at first sight is rather a strange thing. So it lays down conditions under which it is okay for an object to send messages to another object as part of its response to a message. Okay, so this is constraining you if you are writing the method M within the class of an object O. Okay, so what we're saying is, when you want to send messages to invoke methods within your implementation of method M, it is fine to send a message to the object itself, okay, to this. It's fine to send a message to an object which was an argument to this message. It's fine to send a message to an object which this object creates, as in this very method, as part of its reaction to M. And it's fine to send a message to an object which is directly accessible from this object, in other words, using the values of attributes of this object. Okay. What's missing from this list? If we were live, I would ask you what was missing from this list, but we'll see in a moment. No, we'll see right now. In particular, O should not send a message to an object which is acquired by sending another message. Okay, so we shouldn't go something like my P, suppose that's an object which is referred to by an attribute of O, and send it a message get thing. That's perfectly fine up to the get thing. Okay, that is point 4 being used there. But what we shouldn't then do is take the object which results from that and send it a message. Okay, because that's neither one. That's not 1, 2, 3, or 4. It violates the law of Demeter. Okay. And so you'll sometimes see the law of Demeter referred to as the one dot rule, okay, because it's trying to rule out code like that. However, that's not really very accurate, because it's perfectly possible to violate the law of Demeter without having more than one dot on a line. All you have to do is to split the message calls as shown on those 2 lines there. More interestingly, sometimes you have code which does have more than one dot on a line, and it doesn't violate the law of Demeter. And the classic example is if you are sending a second message to an object that was returned from a first message, but the object that was returned was in fact already accessible. For example, perhaps it's the same object that you sent the first message to. So what you have to do is to think about the rationale behind the law of Demeter in order to understand it, rather than at the mechanics, because if you understand what it's doing, you'll find that much easier than having to remember those 4 points and apply them mechanically, and also you won't fall prey to the shorthand of thinking of it as the one dot rule. So what are we trying to do? What we're trying to do is to avoid indirect dependencies of one class on another. Why? Because they may be hard to spot, either from the code or from the models. So you already know that we try to minimize dependencies between classes, but that we can't avoid dependencies altogether, because dependencies between classes is just another word for classes working together, which is what we have to do in software design. Okay? So the compromise is that we say, well, we understand that dependencies are quite dangerous, and it's important that we be able to identify them so that we can sidestep the danger wherever possible. And the kind of thing I'm talking about is, suppose that we have some class B, say, and it changes. Well, one of the things I want to know is which classes, A, for example, maybe A1, A2, A3, which classes depend on B, okay? Because those are the classes that I have to carefully check in order to see whether the change I made to B has done any harm or not. Okay? Now, if it's easy for me to tell which classes depend on B, then that's merely tedious. I just have to do it. But if I can't tell which classes depend on B, then it's dangerous, because I don't even know which classes I have to check. Okay? So the law of Demeter is trying to make it obvious which classes depend on one another. If you write your code so that you obey the law of Demeter, it will be more obvious. Okay? And that's an example there in the next paragraph, which you can read. Do I want to read it out? No, I've already said it. You can pause the video and read it if you wish to. Okay, now here's an example. I've said name slightly changed to protect the guilty. This is mildly adapted from a real design situation which really bit me back when I was a professional developer. Sadly these days that's probably before most of you were born, but there you go. Anyway, so we were working in a setting where it had been made clear to us that we had to limit the use of associations that gave that were navigable in both directions, like the one at the top of the diagram there, between everything controller and job controller, because, it had been explained to us, that makes two classes dependent on one another, and that's a particularly bad kind of coupling in your system. And so the people who designed this were quite proud of themselves for having only one two-way navigable association in the class diagram, which was more complicated than this, but I'm extracting the relevant parts. So what's going on here? The idea here is that we have a bunch of job controllers, and each job controller controls some jobs. Okay, so given a job, there's a unique job controller that controls it. And there's a single everything controller which controls, among other things, all the job controllers. Okay. However, it sometimes turned out that an individual job needed to know which job controller was controlling it in order to send the job controller a message. Okay. But because the designers were so proud of only having one two-dimensional, I keep saying two-dimensional, only having one two-way navigable association, they didn't want to make that association between job and job controller also be two-way navigable. Okay. So instead, what did they decide to do? They decided to allow job, which could already contact everything controller for other reasons, to get hold of its job controller by inventing this extra operation getJC that took a job and returned a job controller, and adding that as an operation of everything controller. Okay, so what would happen would be, if I was writing some job code and I wanted to send my job controller a message, what I would do is I would go to the everything controller, this was a singleton in fact, so I would go to the everything controller and I would invoke getJC with myself as argument, and that would return me a reference to my job controller. Okay, and then I would send my job controller a message. Okay, now unfortunately what that means is that job is exactly as dependent on the class job controller as it would have been if we had just made that association two-way navigable in the first place. Okay, and then we wouldn't have needed this separate get JC operation in everything controller. So it looks as though we've reduced coupling in the class diagram if you only do something as naive as count two-way navigable associations. But we haven't really done anything at all which is helpful. Now, what's the relevance of the law of Demeter? Well, that situation that I just described, where the job code would go to the everything controller and do get JC, and then having got the JC, the job controller reference would send a message to the job controller by using that job controller reference that had just been returned from the everything controller. That code violates the law of Demeter. So if we had been told which is not obvious. Well, it wouldn't be obvious if we only had that as part as the code and we hadn't already introduced a dependency on thing statically further up. It can sometimes happen that you end up with a dependency on a class whose name does not even appear in your code, and that's a particularly harmful thing if you're relying, as you very often will, on search in order to find out what's dependent on what. Okay. So, a bit more generally, what should a method return? So conventionally, many object-oriented methods do return void, so their job is to change some state, not to compute a result. They're commands. Okay. So for example, they're modifiers. They might be set methods, for example. If you're using strict command query separation, as we saw a moment ago, any method either changes state or it returns a value, but not both, and the slogan is asking a question should not change the answer. Notice that the slogan focuses, as I said a moment ago, on the important part of command query separation, which is to say queries should not change state, and then you can use them in OCL constraints because they're queries. However, there are disadvantages to not allowing commands to return values. So for example, it can lead to code that's rather repetitious, which is then cognitively slightly more difficult than it needs to be to absorb. So for example, if you have to set 3 attributes on a class, on an object, you have to name the object for each method call like that. If we allow the modifier to return the object being modified, as well as do the modification, so you write set methods so that their code ends with return this, then we can chain methods like this. So we can go customer dot set first name John dot set last name blogs dot set age 32, and you see this is doing exactly the same as the previous code did, because the reference that we get as a result of set first name is a reference to the very same object customer that we had in the first place, and so we can just use it again to send the next message and so on. Ask yourself why this does not actually violate the law of Demeter. Make sure you understand that. This is an example, simple example of a fluent interface, and they sometimes do violate the law of Demeter in the interests of fluency. What is a fluent interface exactly? It's a bit of a case of you'll know it when you see it with a bit of experience, and I'm not going to say too much more about it. We're kind of moving towards the design of an internal domain-specific language, because the idea is that interacting with an object of a given class via its API should feel fluent, really, should feel like a thing that's like working in a special purpose language that's provided by the API to that class. Okay, so the great thing about design principles and patterns is that there are so many to choose from, and you can't follow all of them all of the time, and indeed I not very long ago set an exam question that pointed out a contradiction explicitly and asked people to explore those contradictions. The important thing is to be aware of what underlies the principle, what motivates somebody to write them down, and then use them as a guide where appropriate. And quite often you'll find that reading discussion of the principles and how they reinforce or conflict with one another is illuminating, in just the same way that reading discussion of patterns is often much more useful than memorizing them. And so I encourage you to do that and to watch out for such discussions.